In this video, I'd like to talk about simplifying square roots, but with variables on the inside. So in this first example, you have the square root of 52x to the fourth. So the question becomes, how do we deal with these square roots, when we have variables underneath? And the general idea, let's say we have x to the sixth, is that we want to be able to simplify this and pull some of the x's to the outside. And one piece of information we can use for all of these is that the square root of x squared. So when you have something squared and you're taking a square root of it, that they both cancel each other and you just get x, assuming that x is positive. Now, if x started as a negative number, then you just have to put absolute value bars here, because no matter what number I plug in here, when I square it, it becomes positive, and then when I take a square root of positive number, that answer would be positive. So let's say you had negative 3. When you plug that in here and you square it, it becomes a positive 9, and then taking its square root, you get a positive 3. So without the absolute value bars, if I just had this equal to x, this would only work for positive numbers. But for negative numbers, if I put the absolute value bars, this is a true statement. But it's only when you put the absolute value bars. Since, like that example with negative 3, when you squared it, you get 9, and the square root of that is positive 3. But if I put in negative 3 in the absolute value bars, I do get back a positive 3. So the absolute value bars make it so that this expression is always true. Now, if you want to drop it, you just have to assume that x is a positive number. But the general idea is that a square and a square root cancel each other. And if you want to see it numerically, if you had 5 squared and you take its square root, this would be root 25, which is 5. So whatever you have on the inside, when you square it and square root it, it becomes that value. So with that in mind, what we want to do is change this into a product of the square root of x squared, or several of them. And x to the sixth, remember, we can rewrite this as just x squared times x squared times x squared. Since they have the same base, so you would just add the exponents. Or in other words, you have 2 x's here, 2 more there, and 2 more there, so in total you still have 6 total. And now when you have a product on the inside of a square root, like let's say you have root 5 times 6, you can break this up into a product of square roots, root 5 times root 6. So likewise, we can do that here. This becomes root x squared times root x squared times root x squared. And then each of these x squares just becomes x, assuming that x is positive. And so you would just get x to the third. And if your exponent is an even number, then essentially when you go through this process, it's just going to get cut in half when it comes to the outside. Now, if it's an odd number, you're not going to be able to pull everything out, and you're going to be left with one of the x's on the inside. But as an example, just so you can see the method, let's say you have the square root of x to the 44th. Then when you actually write out all these x squareds multiplied together, you would have 22 of them. Or in other words, you would have x squared to the 22nd power. And so the square root and the square cancel, and you just get x to the 22nd. Or in other words, once it comes out of the square root, your exponent gets cut in half. Becomes 22 in this case. So that's the general idea, but let's actually try and solve this problem. So let me make some room. You have the root of 52x to the fourth. And when you have a number and a variable expression, my advice is to treat them separately. So rewrite this as root 52 times root x to the fourth. And this x to the fourth we just went through, we're going to replace that as root x squared times x squared, and then we can rewrite it as a product of square roots. Now the square root of 52, well, we have to make a tree with 52. So I need a little bit more room for that, and let's do it over here. So 52, well, it's an even number, so it's 2 and then times 26, and 26 is 13 and 2. So 52 can be rewritten as 2 squared times 13. And since in its prime factorization, one of the primes is squared, we're going to be able to pull a 2 out of the square root to simplify it. So I'll just rewrite this side. We get root 2 squared times 13 for root 52. And then I'm going to break it up into a product. This becomes root 2 squared times root 13. So I'm dealing with the number term and the variable term separately, but they both combine at the end. And then anytime you have a number squared and you're taking its square root, they're going to cancel. So in this case, you just get 2 here. The root 13 is left behind. And then square root of x squared is x. And again, times square root of x squared, also x. So we can combine those to make 2x squared times by the root 13. And now there is this subtlety. This is kind of a deep point here, that when you're taking the square root of x squared, you get the absolute value of x. But since we were able to get back an x squared term, this guarantees that our answer will be positive, since anything you square is a positive number. So that's why I didn't bother putting the absolute value signs. Now, if there was a third one, then we'd have to be more careful here, because then you'd have an x cubed, and that's not guaranteed to be positive. In fact, that could be a negative number. Negative 3 cubed is negative 27. But regardless, this is our final answer here. And so that's what we'd put in the box. We have 2x cubed times by the root of 13. So let's keep going with these. We'll do several example problems.